My sister took French, won the French medal in high school. Hated the teacher. Never spoke it again. Though I mean, like Paris is her favorite city, so I assume wherever I travel to. Yeah, go ahead. Ugh, what can I say? All right, off we go. So I'm kind of going to jump between these two viral PowerPoints today. This is the Cowan PowerPoint for chapter 5, slide 26 for your viewing pleasure to start with. And we looked at this before, and basically we have gone through a lot about the individual viruses and how they spread and how they're classified and roughly the diseases they cause without getting too terribly specific about the ins and outs of the diseases, which we get to in the second half of the program that's there. So what I'm going to do today, this is more about sort of the mechanics about how they replicate, whether or not we'll get to complete prions now, or I will, and probably in an effort to get that done, I might have to send you something, because we'll start something new on Monday. Then on Wednesday, I'll probably do some more review. Yeah, I know, because Sadie won't talk to me if I don't do that. God, this is awful. All right. So these are just a little interesting little nuggets to throw out here, and because there's a few important things that'll go on. You saw I had this slide up before about what happens to this thing called lysogenic conversion. I don't make a big deal out of the bacteriophages for now. In a different context, viruses that affect bacteria are really interesting because they're really going to, I think, down the road be the weapons we use against bacteria because of the limitations of antibiotics and the fact that there's so many problems with regard to resistance and overutilization, resistance, allergies. So in this way, we attack let the virus as it attacks us attack the bacteria that are attacking us. And so and it's something we can study in the laboratory a little bit more easily than you would think, since there's not a whole lot of risk to us. But you can see what viruses can do, and I'll just flip back to give you that other slide I looked at for the context. These are called lysogenic conversion. The lysogen, in other words, can't be reinfected. That's something they call superinfection, or like two infections. And so what happens is whatever the genetic material that the virus carries, and typically these are DNA-oriented uh, bacteriophage viruses, they incorporate with the host genome, effectively altering it, mutating it, whatever word you want to use. But look what it does. It's the toxin for botulism, the toxin for a horrible disease we're all immunized for, called diphtheria. This is really the killer E. coli strain, the 0157H7, and how it kills is hemolytic uremic syndrome. We'll talk a little bit about that. Salmonella, which is a very relatively common kind of food poisoning, just see altering that lipid A component that's there, and the nature of that lipopolysaccharide. Scarlet fever, which we don't see a lot of today, but certainly is a great deal of relevance historically. And these kinds of, and it has to do with how it goes about its business. And strep pyogenes is not an innocent player. Even though you and I just, oh, it's just a strep throat, we can take antibiotics. It's true, but you have to diagnose it and treat it promptly. And cholera, another horrible food-oriented disease that we typically see after natural disasters, war-torn areas, floods. It would not surprise me in what had gone on in Turkey and Syria with the earthquakes and that devastation, whether or not, because that would alter whatever water treatment that they would have available. And typically that's the type of thing you just see. So that's the introductory nugget about the importance of some of the references that we'll be making today. So I'll go back, and this just is a little more amplification. Some viruses carry different enzymes. Certainly the most famous is the reverse transcriptase enzyme that basically reverses transcription, making RNA from DNA, famously in HIV, maybe to a lesser extent, a little less famously in hepatitis B, although certainly not an unimportant disease on a worldwide basis. Not so much here in this country. And again, polymerases, replicases, various enzymes. It's not a lot. It's whatever is essential. Most of the time, they just take over and take over the host cell's activity. So whether or not there's other things that are involved, it is not a big deal. Okay. And so I wanted to go at this is the next part. Okay. This is sort of viral replication in the sense of how it's transmitted to the host, immunological defenses, how we control them. When they say animal viruses, that's sort of code for those that affect us. So it's members of the animal kingdom, if you want to think of it that way, that are there. But for our purposes, that's when we talk about viruses that affect us. That you'll often see the term animal viruses to distinguish it from phage or bacteriophage viruses, which only affect bacteria. Okay, and the replication is differently, and it's all because of that. That stage called uncoding it. They have to attach. And so these are areas where we target antivirals, potentially, not for all, that are able to combat the replicate. Basically, if you interrupt its life cycle, even though it's not living, but if you interrupt this cycle of attachment and growth and replication in some way, shape, or form, or very, very often multiple shapes or forms, you successfully are able to stop the virus. And then effectively, a lot of what we do is to basically it allows your immune system to take over and then effectively rid you or at least deal with whatever damage the virus is doing. So we start with adsorption. That's the attachment process of the virus. Okay, and there's a subtle difference between viruses that are enveloped. They undergo something called membrane fusion. They fuse with the external membrane of the cell that they attach to, versus the naked virus, which is brought in by our old friend endocytosis, just kind of swallowed up. Okay, and in doing so, it penetrates, it enters. Then, interestingly, and this is the distinguishing step, in phage viruses, if you recall that animation of transduction, effectively it just injects the genetic material. Here, the entire ball game comes in. The nucleocapsid enters. So not only is it the genetic material, but it's the protein enclosure. So the process of uncoding, which is unique to how it impacts our cells, okay, was the first thing they attacked. Unfortunately, it didn't work. So what the encoding was an enzymatic activity to break apart that protein enclosure. Didn't work. It was used early, and the earliest antivirals, interestingly, were for influenza, and they were anti-uncoding agents. They really didn't work that effectively. So I do not even know if they are still used. I never had occasion to have patients on them, and it certainly didn't prescribe them. Okay. At that point, once it uncoats, now it takes over. And you get through this interesting phase of synthesis. Synthesis means the genetic material hijacks, for lack of a better term, the internal mechanism of the cell that it's invaded and starts making more stuff. Okay, what's the stuff? It starts making either more DNA or more RNA. It makes protein spikes. It makes capsid proteins. It makes enzymes. Whatever is part of the whatever is are the component parts, and then a la a little assembly line, it assembles it. It takes some genetic material, it surrounds it by a capsid, it plugs in protein spikes. If necessary, it sticks some enzymes into the package, and they undergo a release. And the release depends on what kind of virus it is. Either the virus is in your cell multiplying like a common cold, you get a ton of them, a couple hundred, let's say easy, inside a respiratory cell, it reaches something called the burst size and explodes. And now you went from having one virus to having 200. Those 200 affect 200 cells. And then they all burst, and now you have 200 times 200. So you can imagine how rapidly, other than like the simple binary division that we see, the binary replication dividing in two that we see in bacteria, how much more rapidly, depending on how frequently they achieve this burst size, that they impact us. So, and you'll see, and there's a little nugget about comparing a couple of them there. And then the release will either be they'll burst out, or you'll see some illustrations of what's called budding or shedding. And that typically is enveloped viruses that kind of are extruded. It's sort of like you have a pasta maker, and you put the little thing like a cookie press. No cookie making people. Put the dough in there through the shapes. Love that. Have one for sale on Amazon if you're interested. Just saying, it never hurts to stimulate business. Cook pasta extruder, depending on what you put for dry. Oh, I give up. So the length of the replication cycle varies from 8 hours to polio to 36 hours of herpes virus. And that was what was interesting about polio. And there's a lot of little stories about it. That's relatively short. And polio being a naked virus, that's one of those enteric or pico-RNA viruses you might recall. And what was interesting about them, a kid would, I don't feel great. And they go to sleep at night. And the next morning they wake up, they couldn't move their legs. It was magic in the wrong way, evil magic. That we would see that happen. All of a sudden they lose sensation, typically in the legs to start. And they call the disease infantile paralysis because it typically happened to young people, though certainly not exclusively. And eventually found out, as I told you before, that it was fecal to oral and it affects the nervous system. It basically impacts the nerve going to the neuromuscular. It basically stops that nerve from working that's going to the muscle more or less than anything else. So a virus can invade its host cell only through making an exact fit. So that's where we define the range. It's based on where the receptor is. So the limited range of the cells that a virus can infect, hepatitis B or C for that matter, the liver, polio, intestinal and nerve cells of primates. So it's in this case, polio is primate specific. You might remember last time when I told you about HIV and how we think the origin of HIV was for making polio vaccine. And they basically trapped and utilized sick monkeys to make the vaccine. They gave them polio and tried to harvest the antibodies. It's effectively how they were trying to make the vaccine and trying to tinker with. It's called attenuating, altering the virus. Where was PETA when we needed them? Which I joke around and say it's people eating tasty animals, but I shouldn't say that. It's all right, I'm a carnivore. I have vegans in the family and vegetarians. It's hey, interesting cooking. Rabies, all mammals. Okay, cells that lack the receptors are resistant to invasion. Okay, and I mean now they're looking for certain kinds of tissues. All right, that's fine for tropism, but this is sort of what's happening, where it contacts those receptors, and this will be depicting a naked virus attaching itself and then effectively being endocytosed. That was there. Okay. So penetration of endocytosis, when an entire virus is engulfed. We have in the host cell membrane, that's the membrane fusion. The envelope merges directly with the cell membrane, and in both cases, effectively it liberates the nucleocapsid into the cells. And they're just showing you the distinctions between them, whether we're dealing with something that's endocytosis in a naked virus or this membrane fusion, where the membranes kind of come together. And then in both cases, it enters, and in both cases, it undergoes, as you can see here, uncoated. So DNA viruses in the nucleus, RNA viruses in the cytoplasm, that just makes sense. Retroviruses turn their RNA genomes into DNA. So, and now they talk a little bit about different things with regard to the strandedness, which is not terribly important to us that are there. Okay, you're going to see the way that it is released when the viruses are mature, when they have been assembled. Okay, either by budding, sometimes called shedding, again, it's like an extruder, or the actual cell disintegration, which is a lytic virus, a virus that causes the cell effectively to explode and spill out the little particles. The whole idea of assembly, and this again, all of these are places where we can attack. you're going to see the major weapons we have for influenza and an antiviral are two agents. One's called trade name Tamiflu, and the other one's called Relenza. They're effective early on. Again, it's typical with influenza. First couple of 48, 72 hours tops when they really can attack the advent of influenza. Their target is the release. They attack. You might remember I told you a little bit about those H and N markers. The N marker, the neuraminidase, they inhibit that, and the neuraminidase permits the release of those agents, of the influenza agent. So all of this is utilized. So, and then we have things that impact assembly, things with HIV that affect that retrovirus aspect of it, the DNA, the RNA reverse transcriptase. Most of them occur not so much in the assembly, but if we go backwards, it's sort of in the replication process. Okay, it's basically where we're either assembling DNA or RNA, which become the genomic core, the genome of that particular virus. That's where the stuff comes from. And we impact that with what I like to call lookalike drugs, which are analogs. So they're analogs for the guys you're already familiar with: adenine, thymine, cytosine, guanine, uracil. And what does it mean by an analog? Basically, they're the same molecule with a toxin that's been attached in the laboratory chemically to it. And viruses grow so rapidly, they suck up the stuff. It's the same principle as cancer chemotherapy. We're going to use what are called antimetabolites, basically agents that are gobbled up that will kill the molecule, kill the virus, if that's such a thing that can happen, kill the cell, particularly with cancer. And that's why it's such a valuable thing to understand. So assembly, putting the parts together, that's called synthesis, and release. Okay, size of the virus, health of the host cell. Pox viruses, 3,000 to 4,000 virions. Polio, 100,000 virions. Okay, immense potential for rapid viral proliferation. So imagine how short that process was, only 8 hours, and you're releasing, 10 to the fifth particles. And so that's theoretically 10 to the fifth more cells times 10 to the fifth, which is 10 to the 10th, which is an immense number. Okay, it's like 10 million all of a sudden. So this is an actual micrograph of this budding process, the maturation and release. Effectively, here's the nucleocapsid. You can see what's happening as it comes in contact with the membrane. It picks up spikes that have been effectively manufactured and incorporated with the membrane, and they become the envelope as it's sort of spit out or extruded, budding or shedding. So what happens? Understand that cell is never going to, you might get better from a virus. Your cell will never get better from a virus. It only has one of two outcomes. It's either going to die because it's going to explode, or like this, it's going to become a viral factory to constantly spit it out. So the idea that the organism can survive the virus, but the cells that are infected are always impacted. And that's the tragedy of, let's say, HIV or other disorders, where we see permanent changes. And effectively, that cell line becomes a constant process of manufacturing altered cells. And that's why that slow transition, why we classify it as a slow virus, of going from being HIV positive to AIDS, because the single most important cell in your immune system, the helper T cell, is the cell line that's affected. And finally, you get to a critical number of insufficient helper T cells, and at that point, your immune system don't work no more. We used to say in my old neighborhood. I know that's a series of double negatives. Yes, ma'am.
So, like with latent viruses, do those cells that become factories, do they just slow activity, or
they just stay as fast? They're there. Whether or not the virus does anything is the question. A true latent virus, it's just incorporated. It's not active. So that's a cold sore. That's shingles. You were exposed to the chickenpox virus, either by immunization or having the disease. And something has caused your immune system to falter and permitted that virus to express itself. And when it comes to that, there's so many things. The most common things, we look at stressors. And stressors can be physical, emotional, medical. Uh, I've seen them after accidents. I've seen them after loss of a loved one. I've seen them after just under high stress situations. My wife, when she was in nursing school, take this to heart, used to periodically before an exam get a big old cold sore here. She was so stressed out. It's crazy. So everybody, it happens differently. So that's really what true latency is. It's there, and sometimes it never expresses itself. Somebody can a, get a wart on their foot, have it, it goes away for however, either it goes away by intent or goes away by itself, never shows up again. Okay, the same thing. They can have a cold sore once, never comes back again, or they can have one that's chronic and recurrent. It just depends. And I don't know that we have a track on what's involved with it other than to generically say stressors that are there. And I have seen some buttes to that type. I always think that the secret to health is health. I know that's kind of talking in terms of yourself. Your best effort is to stay healthy for the most part. I don't do it all the time, but we should. I mean, I used to get colds constantly because I smoked like a chimney for 40 years. You know, so I'd be sitting here and whether I was practicing and coughing. If I got a cold, last for months, constantly bringing up some gross. Yeah. Okay. I always smelled like a cigarette when most of the time, as my ex-wife used to tell me. But the reality is that I think that help, and for a lot of us, particularly older individuals during the COVID era, we stayed pretty healthy. I like to think. I think my wife and I both got it at one juncture, and it was relatively limited comparatively speaking. And I think that's a tribute to and what's health, nutrition, being to some extent physically active. Thank goodness we're walking the dog. Well, he's walking us. Does that answer it? Yeah, more or less. Adsorption. So it adsorbs. That's just fancy for attach. So adsorb is attachment, where absorb is to engulf something. If you want to look at it, okay. So when you get to digestive, kind of like what cholesterol does, not cholesterol, kind of like what fiber does. Soluble fiber in your diet basically picks up fatty molecules, high cholesterol laden products, and they kind of ride their way out so you can excrete them. Okay, that's adsorption. It's sort of like you're grabbing on and look you're running and you catch the bus and you jump on, like the old days, like a streetcar. Ringing a bell. Go to New Orleans. I love streetcars. They're very entertaining. The hotel we stayed for you guys of a literary note. The hotel we stayed at in New Orleans on St. Charles Avenue, which is the Hotel Pontchartrain, this very old, elegant 1800s hotel. It's home. That's where Tennessee Williams wrote Streetcar Named Desire. Most of you should have encountered sometime during your earlier education. Okay, I'm not talking to you anymore. Major role for Marlon Brando. So adsorption. So it attaches. Usual proteins require for its normal function. So the membrane receptors that virus attach to are usually proteins the cell requires normally. Spikes on the envelope or how they facilitate it. Penetrates and uncoats. It's either endocytosis, like I said before, or membrane fusion. Doesn't really matter. Then this whole process, building blocks. So, and they give you the laundry list, whether it's negative or positive. And you don't go crazy for this. Bottom line, proteins for the capsid spikes, enzymes are synthesized on the host ribosomes using the host amino acids. So it's taking over. Then they are basically assembled. And here capsid is first laid down as empty shell, serves a receptacle, blah, 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 blah. And then released. They leave in one of two ways. Non-enveloped or the complex ones, which would be more in the bacteriophage line, reach maturation in the cell or released in the cell lysis or ruptures, enveloped, budding, shedding from the membranes of whatever structure they're budding or shedding from, pinching off a little pouch, so to speak. How do viruses damage you? Bacteria, most of the time, their damage is toxins. Sometimes their damage of the toxins is what's called indirect, and we're going to get to that. And probably after break, we're going to start looking at that more intently, the way that bacteria and viruses hurt you. Indirect means through your immune system. So you saw that one about scarlet fever. That's a toxin, but that toxin is what's called a super antigen. It basically causes your immune system to go crazy and produces lots and lots of chemicals that cause all the damage that are there. Viruses are a little bit different. Okay, they damage cells, and for the most part, and the other aspect, when those cells are damaged, they provoke the immune response as well. So COVID, the context that a lot of people have, most of the time the damage was twofold. It was damaging certainly the respiratory cells, but the products that were being produced by those cells because of the COVID invasion were pro-inflammatory agents. They caused an immense amount of inflammation and an immense amount of response by your immune system. And that's why in certain individuals it fulminated. That's what's sometimes a hard thing to understand. Sometimes being healthy is a problem for certain diseases. That's the classic example of the worst of all the killers microbiologically, the Spanish flu between 1918 and 1919, which historically, and it depends, and I've read books about it. And there's a wonderful book by the lady who, I don't know if she is or was the lead science writer for the New York Times, called Flu. And it's one of those like thin books. It's kind of like Tuesdays with Maury, that kind of thing, kind of book. Okay, and she kind of wrote almost like biographically about this flu, and all the way that they tried to analyze what it was. Fascinating, and it's a couple hour read, so to speak. And what happened with that is it wasn't the very old and the very young. That's typically who influenza clobbers, because you get very, very sick. Your immune system goes wacky. Vomiting, diarrhea, fluid and electrolyte, respiratory problems, and sometimes they succumb, unfortunately. The Spanish flu was young, healthy individuals. The tragedy was these were a lot of men who had come home from survived a horrible war, World War One, and that very next winter died. And so they were young, healthy individuals, which was really the antithesis. And why was that? Because their immune systems were strong, and so they became overly responsive. So it's a very, very, and we saw a lot of that with COVID, unfortunately. Certain people, exactly what the genetic basis was, why they responded to it. I don't know if that's been thoroughly studied. So it's interesting in that regard. So cytopathic means how it damages the cell. So changes in shape, intracellular changes, inclusion bodies, okay, are things that we help to identify. They're going to damage the cell. They're very useful when we stain them to be able to identify whether a virus is invaded. When someone gets a wart, a genital wart, how do we know it's a genital wart? I mean, it looks like one, it acts like one. Diagnostically, you have to be able to see inclusion bodies staining, and you might remember this, the stratum granulosum. That's the diagnostic criteria. I mean, I treated and removed thousands of them. Okay, because I could certainly tell you what it looked like in any way, shape, or form. I can't make that diagnosis without with the aid of a mic. I can take all the pictures I want, but legally speaking, it has to be diagnosed pathologically. Syncytia, respiratory syncytial virus, a fusion, damaged cells basically become these giant cells, and in the lung, very difficult to breathe. So just so that it can be that, or they weaken the, when you hear about hemorrhagic fever, They weaken the capillaries. Blood leaks out, leaks into organs. The organs, clots develop, they die. So there's some interesting things. Very important are the idea of what are called persistent infections. Most of the time, and the way we typically demonstrate it, and you're going to see this a lot, it's my favorite, it's a trapezoid. Can't beat a good trapezoid. That's marker. That trapezoid. You can change the shape, but it's still trapezoidal. Most of the time when people get sick, you have basically, it develops, okay, you want to call it incubate. You have the disease itself, and you get better, what we call convalesce. That's typical for an acute, and how long you're sick really determines it. Okay, so things typical, a common cold, you get sick fast, lasts for 7 to 10 days, you get better. Everybody knows that. That's a typical acute infection. When something persists and you don't get better quickly, and there's certain variations that are there. So sometimes it can be you can have a very slow, very elongated, and a very long recovery. They talk about this long COVID. To me, I don't know if that's the same thing, but basically it's having symptoms persisting for a long time. You hear a lot, oh, I see so-and-so suffering from long COVID. I don't know if that's necessarily what happens, but it kind of gives you a context for this. What happens in latency, let's say you get a cold sore, standard oral herpes, cold sore, nothing major, goes away. Latent means it's gone, and then all of a sudden it comes back. Why it comes back? Again, variety of reasons. But what exposes it to no longer be latent or allows it to begin to replicate. That's another aspect. So that's classic latency. When we look at this, sometimes some people don't really get better. In the sense, they call this a true persistent infection. What does it mean? You're always releasing the viral particles. So when you hear about a chronic viral infection, and the ones that are classic for this are hepatitis B and hepatitis C, that's what you're worried about. When someone has chronic or persistent hepatitis C, which you may encounter, that means you're always at risk. Their secretions are always going to have viruses. That means if you somehow get a blood splatter, if you have a cut, if they're combative and scratch you, you get their secretions, if you will, on you, you've got trouble. I'll tell you the anecdote about my wife is my wife, her hair has always been a very important feature. And they were trying to get this lady into a potty chair. Guess what happened? She let go. Right on my wife's hair. And she was a nurse's aide or a nurse. That was quite an event. And then lastly, the oddball of this is sort of a variation of latent. This is what HIV does. It doesn't stay latent. It gradually starts to climb very slowly until it comes back, and then it persists forever. That's a classic slow virus, typically slow as 2 to 10. So there's a lot of different little subtleties in these viruses. Thankfully, most of the things that affect us, they come and they go away. Stomach flu, which isn't a flu, by the way, but an enteric virus, okay, you get it, goes away. Usual stuff. Watch what you eat, be careful, blah, 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 that type of thing. So, a few weeks to the remainder of the host life can remain latent in the cytoplasm. There's a lot of differences. The incorporation into the DNA of the host. So, measles can do this. The fancy name we give this is called provirus. Okay. So we can see alterations. There's an odd thing that occurs in measles, very rarely, 1 in a million, where it causes damage to the brain. It's called SSPE, subsclerosing panencephalitis. So something in the genetic alteration, very rarely, but it can happen, will cause people to die, effectively cause their brains to die, to become inflamed and die. It's relatively rare. Okay. Chronic latent state, period, become activated under the influence of various stimuli. Here's herpes simplex 1 and 2, herpes zoster. Classic examples of that. So those are little nuggets that go with it. This is maybe the one that's most interesting. And there's a slide in the other PowerPoint sequence that talks about the viruses that are associated with cancer. And once again, I will tell you that the predominant force in this is human papillomavirus, because there's just a lot of strains that unfortunately lead to genitourinary cancers. So it's tremendously associated with cervical cancer. It's not exclusive to women. Okay. The skin and tissue of the male external genitalia is not, the skin is very soft and delicate. It's almost close to being mucosa like. That's why so penile cancers and related areas in there are certainly abundant. And we see it in other areas. There's a tremendous amount of HPV that has become very common now in oral carcinomas because of let's say the greater impact of oral sex. So, and we're going to go over all this stuff again, but this is what's out there. Okay. So I said 15 to 30. This textbook, 13% of cancers are caused by viruses. For your purposes on the exam, 15 to 30 is the answer. If you see a question that's 15 to 30, choose that answer. Will you do that for me? Thank you. Don't tell anybody who's not here. See, I don't feel comfortable doing that. I give up. No, why? So they undergo a kind of transformation, not the same as transformation of bacteria. Oncogenic, onco means tumor, genic means making one, virus. It's not, effectively, we'll call them cancer causing. Some viruses carry genes that directly cause cancer. I'll buy that. Okay, other viruses produce proteins that basically impact the growth cycle. They fall into two categories, and some that are particularly oncogenic use both. Maybe I told you you guys could read it if you want. You want a Pulitzer Prize maybe 10, 12 years ago. It's basically cancer is a biography. It's called The Emperor of All Maladies. It's brilliant. I saw the guy interviewed on TV. Brilliant. His last name is, I'll get you the reference because I have it in my iBooks. There's two. This is what when the viruses target these two areas. One are called, nice marker, oncogenes, and the other, okay, tumor suppressor genes. And we have genes in our cells that help to govern the growth cycle. These are two of them. So effectively what cancer is, and I say it all the time, is when the growth cycle, when the cell cycle gets out of control. All those cycles they go fast. Our controls hold them. We govern that. You remember this, if you remember the cyclin and cyclin dependent kinases of the cell cycle, which you should have had. If you had me, you certainly got that. Okay, there's certain checkpoints, is the way that they were described in the cell cycle. They don't allow it to proceed, particularly if the cells are either not formed properly or there have been errors in DNA and likely to form cancer. These are the things that govern it. We have normally what are called proto, which means pre-oncogenes. Okay, that means they're in the off position. They don't make tumors. They govern the cycle. When the virus comes along, okay, it impacts it. It changes them to oncogenes. Okay. The analogy is as though that's in your car and you're driving, and it's as though your accelerator got stuck. You have a normal accelerator that you can control with your foot, and all of a sudden, it's going on its own, and it's just getting faster. That's an oncogene. A tumor suppressor gene, okay, is usually on. Tumor suppressor genes are usually in the on position. They're your brakes. When the virus comes along, and oftentimes does to both, now all of a sudden the tumor suppressor genes are in the off position. What that means? You lost your brakes. So now you got an accelerator pinned to the floor, and your brakes don't work. You're going to crash. That's when you hope there's a big snow mound and you can get a soft landing. Having lived up in northwestern Pennsylvania, I've had to do that a couple of times. You ever get on a stretch of Route 8 that takes you up toward Franklin and Oil City? Coming down that hill, got black ice on it. Soft landing, please, I'm dying. My first wife yelling, "Why aren't you home?" "I'm in a snowbank." And then some other words. Okay, that's the idea. So remember, oncogenes, which are usually in the off position, called proto-oncogenes, and tumor suppressor genes, which are usually active and become inactive. That's it. So those cells are transformed. Growth rate, change your chromosome, surface molecules, divide indefinitely. The mammalian viruses where we see this, the ones that are of significance to us, and they should have hepatitis C in there as well. Okay, hepatitis B virus, because those cells already replicate like crazy. And when they're virally damaged, they even replicate more. So B and C are both associated with hepatocellular carcinoma. Herpes, we've talked about. Okay, the Epstein-Barr virus, the HHV8, the Kaposi sarcoma virus, we know about, definitely associated with it, and papillomaviruses like HPV. This is called HTLV1, which is a retrovirus. I don't know enough about it. It's definitely in the pack. I don't ask questions about it. So, and then viral oncogenes incorporate into the host cell and produce proteins leading to uncontrolled growth. So these are some retroviruses. Viral genes affect expression of host oncogene leading to uncontrolled growth. Okay, retroviruses, DNA tumor viruses basically affect the DNA. So there's a variety of ways that these can all induce different cancers that are there. So it's terribly important to understand. These are the bacteriophage. Most of them are double-stranded DNA. There's some oddballs that are in there. Every bacterial species is parasitized, means occupied at times, by various very specific bacteriophages. And so often what happens is there, like we were showing before, with those toxins, they're more pathogenic. The difference is effectively this being the head, which is effectively the capsid with the genetic material. All this other stuff, okay, basically is a means to inject no capsid, just the genetic material. And then it can go in different directions. And it's a little confusing, and I don't do it anymore. Okay. If it becomes latent, the name we give to latent viruses and bacteria is lysogenic. We call that bacterial cell the lysogen. Okay. Not that I'm not going to ask you about it, but effectively, if you see, that's where the term lysogenic conversion is. That lysogen, if it's the right kind of virus, can change that bacteria into one, let's say, makes a toxin. And then they have different things between temperate and lysogeny. And so prophage, which is the incorporated virus in a lysogenic cell, becomes activated and sometimes can cause it to replicate or burst, things like that. So this is, and it's occasional, I'll buy that, but that doesn't mean it isn't significant or impactful. That's the and this you should know. Lysogenic conversion, when a bacterium acquires a new trait from that particular phage. And when they say temperate phage, that's a phage that just incorporates, doesn't cause it to burst. And again, just a short list of the toxins that are involved. Not a whole lot. I don't do any of the cultivation from these. This is all about vaccines that are there. Most of the time we use basically use bird embryos, so they're grown on eggs. And one of the things you have to worry about with vaccines, once they're grown in eggs, is that people have an egg allergy. So it's something, if you have or know somebody with one of those, that's a question to ask, because then you need specialized vaccines for that. And sometimes they grow them in tissue cultures as well. So that, I mean, that's, that I don't do that particular nugget. The bird embryos are really the way that it's done. Typically, it's chicken or duck eggs are by far and away the most common ones that are utilized for that type of thing. Bacteriophage, when you see, we don't do them in our micro lab. For you folks, some of the folks who are doing some research might be using these, and they show up at these plaques. It shows where the virus infected bacteria have been destroyed, and they're clear patches. And so it's visible manifestations of the effects. So, I mean, here you might see normal infected culture. Here you can see a culture that doesn't have, where you see those plaque areas that are there. I'm seeing if there's anything else. Yeah, I don't want to give it short shift, so I think I'll probably stop. I will send this information to you. Prions, I was just watching a show where they were talking about infected blood. It's a wonderful show. I love British crime shows from England called Silent Witness. There's like 26 seasons of it. It's great. And it stars Amelia Fox, who's absolutely fabulous. But long story short, they were talking about this being passed from transfusions to people, which was scary. Okay, I wouldn't suggest that you have to worry about it, but we'll get into it. So I will probably send you. It's a very little brief presentation on prions, and that pretty much concludes the viral chapter and the chapter for and the information for the exam. Bye. Have fun.